All right, you feel recharged?
No.
No.
Yeah.
Excellent. Excellent. All right.
Oh, yeah.
Water here. So, for sure. Oh, yes, without saying. So, we were fixing some TI issues during the break there. It's funny. I was going to say something about before you graph your graph, make sure you don't have anything else turned on that might get in the way of your graph. And boom, I've got some of you were asking, where's my diagonal line that you have? You shouldn't have it. That's left over from my Math 105 class today. So what I'm going to do is I'm going to press y equals and turn that line off. That's what your clear. That's what your graph should look like, and it shouldn't have anything else in it except that. That's what your graph should look like. Okay? So if you have anything else in it, if you've got like a parabola or a squiggle or something like that, just press your y equals button and look through here and make sure nothing else is turned on. And that's what anything else would be. Cool! So the question we had originally was, what does the data look like? And a couple of you said bell curves, a couple of you said we had no idea. Corey said, I think the average is going to be to the left of the y-axis because the average is negative. I see all these things. So the bell curve was a beautiful, beautiful choice. The left of the y-axis average was a beautiful choice. The one thing that I don't like about this graph, whenever you press zoom 9, it will always give you space for 7 bars. No more, no less. So you see there's a bar here, 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 and a space here. Now, the TI does this by default. That is what zoom 9 does. Zoom 9 takes the x of your data, the lowest number and the highest number, takes that distance and cuts it into 7 pieces. That's how wide it makes the bars. So if you would, friends, please press the trace button. Trace is just to the right of zoom, just to the right of zoom. And a little spider appears, a little tiny spider appears. And that spider, don't kill it. That spider tells you that in the range between negative 58 pounds and negative 44.8333333 pounds, there is one data point. One data point, okay? If you would, hit your right arrow button, scooch one to the right. It now tells you between negative 44.8333333 pounds and negative 31.666666 pounds, there are 3 data points. And if you keep scooching and going, there are now 12 data points between negative 31.666 and negative 18.5. It's going to keep doing this. It's going to keep doing this for all. I have no problem with that. The problem I have is these are kind of illogical numbers to use, aren't they? I mean, they're goofy fractions. And they're only goofy fractions because that's how the TI divides up its range. So what I like to do personally is I like to get in there and kind of mess with it. Once I have the window close like this, I then like to go back in and mess with the window, customize it, and make these more logical. The way you do that, I call this finagling the window, and we'll talk about this frequently as we go through this course. Press the window button now, if you would. Window. Look at these numbers. They're kind of goofy, because a computer came up with them. A computer did this. It said, oh, you have this to this, I'm going to make it this. It just divides it up using an algorithm. But you can go, ooh, I gotta show this to my boss, and my boss hates math. Maybe I better make the numbers nicer, right? So I think we should do that. You see this? Whoops. This negative 58? Let's make that a more like easy to digest number. How about negative 60? That's a little bit easier to digest, isn't it? I think it's a multiple of 10, which we seem to like better. Negative 34.16666. We'll call it 35? I love that idea. Multiple of 5, you can also make it 40 if you wanted to, but I think 35 is fine. X scale. Now this number here, this number represents the width of the old bars. So those weird numbers, the negative 58 up to whatever it was, negative 36.666, it's that wide of the bar. I say let's make that a more logical bar width. How about 10? Oops, 10. Now, leave the y's alone. Leave the y's alone for now. We might want to mess with them too, but just leave them and now press the graph button. Graph. When you press the graph button, oh, look at that. Oh. Now, how is it it the same as the old graph? How is it the same? It's still a histogram. Boom.
The curve is still.
Say that again. Say that again, Sandy.
The curve is still on the left, and it's still in the same spot.
Good. The curve, Corey's average is still. Hey, let's find Corey's average while we're here, shall we? Where would you have to put your finger to balance this plate of cookies? You tell me. I'm going to stop.
There.
Believe it or not, it's right there. Now you know it has to be because you have two pieces of information about this curve. Number one, you know the average. Ha! It's negative 15. And you also know the scale of what you put down, right? You know the scale is 10y. I just put up two fingers, I don't know why. It's 10y. So, under-caffeinated apparently. If that's 0, that's negative 10. That's negative 20, right? Which means that guy right there is your x bar of negative 15. Very nice, Fred. Now you were damn close when you said it was over here. That's the mode, right? And the modal bar is higher, but that's because the mean, median, and mode aren't exactly equal except in perfect bell-shaped data. Except in perfect bell-shaped data. This isn't perfect. It's bell-ish. That was my next point, is I still think it's close to a bell curve. It's not perfect, but data never is. When data is perfect, you know what happens? Harrison Ford tries to get killed by the one-armed man, running for his life because he killed his wife. That's what happens when data is too perfect. Some of you have seen The Fugitive.
I've seen it.
Some of you have seen The Fugitive. Yes. The reason who has not seen The Fugitive? Go watch it. It'll make perfect sense what I just said. All right. Anyway, x bar is negative 15. Okay. So, and hey, you can totally finagle with these windows all you want. Watch this. If I change the x, I'm going to put this back. So if you don't want to mess with yours, that's totally fine. If I change that x scale to 5 and then press graph, notice what happens.
They get tiny.
They get tinier because now the bars are only 5 wide. But notice the average is still at 15. Negative 5, negative 10, negative 15. It's still right there.
Don't do 1.
What happens when you do 1?
Error.
You get an error. You can get 2. This is a TI issue. It doesn't like it when you make the scale too small. You can knock it down to 2, for example. And you can't knock it down to 2. See, and I don't know what algorithm it's doing. Make it 3. Okay, 3 works. But if you make it too small, the TI gets pissed. I don't know what too small is, FYI. I don't know what that number is, what too small is. But I like your guys' 10. I think your guys' 10 was great. I think it's fantastic.
10?
Yeah. So that's a scale of 10. That's what we just had original. Now, what I want to do is I want to find those standard deviations on this graph. I want to find those 16s on this graph. Because Andrea, tell me again how you applied that 16 when I asked you about 10-15 minutes ago about it.
That it can vary from negative 15 by 16 pounds above or below.
Thank you, my friend. That was perfectly said. If we would, friends, let's apply that 16. Riley, you guys got a margin of error before as well. Let's treat it like that. Let's act it as a plus or minus from the average. Joanne, go ahead.
So why does it sound like it's the margin of error?
You can interchange it. Do you want the quick answer? I'll give you the quick answer. A margin of error is used when you apply a sample's data to talk about your population. That it becomes a margin of error. There's a calculation you have to do, which we're going to learn in 243. I promise you this, Tara. I promise you this. I promise you. Right now, we're only looking at this sample's data. This sample's data right here. That's when we talk about just S. There's no margin of error in a sample because the margin of error is only when you're trying to apply your sample to a population. That's when you have error because you might be wrong. Assuming they act the same way. It's just the definition is different. There's no error in a sample because you know what your sample data was.
It's confined.
Exactly. You're confined to just your sample, which means you're also limited with what you can say about your sample.
Right.
But one step at a time. Let's get this down first, then margin of error will make even more sense. So let's do just that. Let's add and subtract 16 to x bar. Okay, so if I start at negative 15 and add 16, I get up to about here, yes? Now in symbols, that would be x bar plus s. All I did was I added s to x bar. If you don't like symbols, call it 1. Because it is, right? It's the number 1. Fair enough? And in symbols, if I knock this down by 16, That would be negative 31?
Yeah.
Okay, so 10, 20, 30, it's about right about here. In symbols, that would be x bar minus s, which would be negative 31. Now that range of values between negative 31 and 1 is very, very, very well known in statistical jargon. You've probably heard it if you've taken a psychology course or sociology course, an HDFS course, a natural resources course, a nursing course, I would hope, definitely a business course. It is called, and this is an unfortunate term, kind of, one standard deviation from mean. Let's put that over here on the sideboard. I just said board. Board. So, one standard deviation from the mean. One standard deviation from the mean. One standard deviation from the mean is a range of values. It's a total range of values that starts at the average minus the standard deviation. That's the starting value of the range. And it goes up to the average plus the standard deviation. There's a whole bunch of numbers in there. There's a whole bunch of numbers in there. The lowest one is negative 31. The highest one is 1. Give me another number in that range.
20.
20. No, negative 20. Negative 20, that's what you meant. Yes, negative 20. Give me another number. In that range of numbers.
0.
0. A very important number is 0. Good, good. Negative 20. 0. Another one. Negative 7. Give me another one.
2.
Negative 2. Negative 3. Give me another one.
1.
1. Give me another one.
0.5.
0.5. I was thinking that one. That's crazy. That's crazy. 0.5. See, all these numbers are in that range. That's what one standard deviation is called. If you guys would do me a favor right now at this point, would you go back? We're not often, we can't do this. I shouldn't beat around the bush. You can't do this in general, but because you have the raw data in front of you, you can. Go back into your raw data and count how many of those numbers are in that range of one standard deviation. Okay, go ahead and count. Count it up.
31 to 1.